Hello class, and welcome to Module 2, where we are going to be going over the biomechanical principles of human movement. So a brief overview of what to expect from this module. We're going to go over force and torque fundamentals, lever systems and mechanical advantage, balance and stability, momentum principles, and mechanical loading on tissues. So why this matters. So we're going over from structure to mechanics. So we're going module 1 focused on the structure, so what moves. And now we're going to focus on the how and the why. So going more into the mechanics and how focusing more on the force produced by our muscles and how this produces torque around our joints. So why this matters? This can help improve performance efficiency, reduce risk injury, and informs exercise prescription. So being able to understand the how and the why the movement is occurring can help you be more specific and tailored when it comes to your preventative care or rehabilitative care for your patients or your clients. So there are different variables that can alter or affect your body's ability to move, the how and the why, and then of course injury prevention or injury risk. And these variables are torque, force, torque, levers, balance and stability, momentum, and mechanical loading. And we're going to go more into these specifically throughout the rest of this module here. So we are going to go first into force. So in human movement, force is responsible for initiating, sustaining, and controlling all motion. Without force, no movement would occur. So again, force is that push or pull that changes motion. This force can have two methods of being applied. So whether it's coming from internally, which is it's only by our muscles. Only muscles can actively generate internal forces. But tensions in our tendons, connective tissues, ligaments, and joint capsules may passively generate internal forces. However, muscle contractions are the only ones that can actively generate internal forces. So the ability to have that push or pull to change motion. So muscles being able to change the position of our joints, of our bones, to be able to do a bicep curl, to be able to do that movement. And then we have external portions, or external forces, and this can be gravity, resistance, ground reaction forces. So these are produced from outside the body and originate from these variable applications. We'll go over a little bit more about that as well, but about each one in particular as well. And then force can have magnitude, direction, and a point of application. All of those matter when it comes to the force that is being generated and the force needed to overpower the force being generated. We'll go over into that a little bit here. All right, force can have direction with it, so it can either be linear, so having a straight line, or it can be rotational, where there's going to be angular movement that produces what's known as torque, which we're going to get into a little bit in here in a second. But just to note, most human movement is rotational, because again, force has a direction and point of application, which can influence the movement patterns. A change in force direction can alter the joint mechanics and the muscle activation patterns. All right, and now there can be two different types of forces. There are static forces and dynamic forces. So static force is force without visible movement. A great example of this is a car parked on the side of a hill. So the static friction between the rubber tires and the road perfectly offsets the gravitational pull to help keep the car stationary. So having that car in parked, forcing that, having that force exerted against the tires and again the road, preventing it from sliding downward. And then dynamic force is when the force is producing motion. So this applies significantly to the muscles that to the type of contractions that we produce from our muscles that we reviewed previously in Module 1. So a dynamic force is an unbalanced force that causes the motion to accelerate, decelerate, or change its state of motion. A great example of an applied example of a various type of external force will be gravity. So gravity acts downward constantly. And so our muscles must counteract that gravity so that way we can stand upright, we can walk, we can jump, we can move. And so alternating the body position changes the torque demand. So again, torque is the rotational equivalent of force. Again, we're going to get more into that specifically here in a moment in this module. And then we also have ground reaction force. This is another external force placing demand on the body. And so this is the force exerted by the ground on the body. So it opposes gravity during standing and jumping, critical in biomechanics. So a great example is running on the track versus running in the sand. So it's easier to run on the hard track than on the sandy surface because the difference in the ground reaction forces between the two surfaces. The track is going to be able to resist the runner's force when trying to run forward, while the sand will dissipate the force and it doesn't have as much equal ground reaction force being exerted back onto the body. And so that causes the runner to experience reduced speed and forward force when trying to run on the beach. And so here is a review what we've gone over thus far. So the types of forces in human movement based on movement produced, we have linear forces, so produces straight line motion, and rotational forces that produces that angular motion known as torque. And then we have different types of forces in human movement. So the review here, we have internal forces coming from muscle contraction, and then joint reaction forces, the body's ability to react to the forces being applied to it. And then we have external forces such as gravity, ground reaction force, and then resistance. If there is an external resistance being applied to you, if someone is pushing against you and you're having to push back to withstand that pressure or withstand that force. And then based on movement condition, we have two different types of forces or in regards to movement. So static force, no visible movement, but force is still being applied and still being produced. And then dynamic forces, there is an unbalanced reaction of forces, and so now we have movement. So those are the two reviews there, and now we're going to go into our knowledge check. So in regards to force, so when you are curling a bicep, and you're curling a dumbbell for a bicep curl. So is this internal or external force? Or a mixture. You know, you have the external force of the dumbbell having the external force of gravity, but then also the internal forces of the muscles having to produce that contraction to be able to produce that movement. Is this linear or rotational? So is it producing a straight line, or is there a rotation around a joint axis? All right, and now we are going to dive deeper into what is torque. So torque is that rotational effect of force. Because most movement occurs around the joints, torque determines how effectively a force produces rotation. This occurs around the joint axis, and it depends on the force magnitude and the distance. So torque is calculated as the product of force and the moment arm. So the moment arm is the perpendicular distance to the axis. So I have a little picture here to help show you. So you have the joint center, so it's just going to be that perpendicular distance. It's going to be that moment arm. And so then you see how you have the lever and then the muscle force. So the greater the force or distances increases the torque. The joint angle increases torque demand. And so here is an example of changing that joint angle and how that increases the torque demand, because it's going to change that moment arm. So right here, having the joint center, the joint axis right here in the center, everything is balanced. That perpendicular is balanced along with the force. But then when we move it just slightly, where now you're holding it at a tilted angle, that joint center, that axis changes. And so it slightly increases the moment arm, the distance, that distance there, or that perpendicular distance to the axis, that moment arm to the force that's being generated by the weight of pulling against the gravity as well. And then that moment arm changes even more so when you're having to hold it at an even greater angle downward. And then here is another extreme version where you're having that joint axis even further down, but then also now it's increased in distance. You're having to hold like a longer pole with the weight at the end. That moment arm is increased. And so now the torque is going to be increased. So that torque demand has been increased. So going a little bit further into that moment arm. So again, the moment arm is the distance from the joint axis to the line of force. It changes with the joint angle, and it alters the torque demand throughout the movement. So this distance, that moment arm, that distance is critical because it can directly influence torque production. Even if the force remains constant, changes in that moment arm can significantly alter the torque and the demand that you're having to, or the force you're having to put into it. As you saw with the previous example of the guy holding that barbell, and then the various changes in the position of the barbell and having to maintain or hold it in a steady position, that changes in the torque demand because of the moment arm increasing. Another example is during a bicep curl. The torque is the highest when the forearm is parallel to the ground because the moment arm is the longest, as you can see here in this example here. So doing, this is your humerus, and then you have doing a bicep curl here. So you have, this is EMA, the external moment arm. So the moment arm, the joint axis, and then the force that having to hold or force react against gravity, and then holding a dumbbell potentially, so having that force being applied downward, and then your moment arm is that perpendicular distance. But when the forearm is parallel to the ground, the moment arm is the longest, as you see here, versus if your forearm is closer down towards the ground or if it's higher up towards your body. So the moment arm is going to be longest here. And so as the arm move is closer to vertical, the moment arm shortens, reducing the torque demand. All right, so going further into torque across the range of motion. So as we've already gone over, torque varies based off the joint angle as that changes. And peak torque is generally about mid-range of a joint's motion. And this is because the moment arm, the leverage, that position creates the longest of the muscle fibers. And so they're at an optimal length to create more force. This is going back into the length tension relationship that we learned about in module 1. Because muscles can generate the most active tension when they're at their resting length. So an extreme shortened position, so if the muscles are shortened, there's an overlap of the actin and myosin, so there's less force production being produced. There's going to be less ability for them to be able to grab onto each other to create those cross bridges, versus when they are at a more resting position, a more optimal length, they can produce more force. And so this can explain why you can have sticking points in certain lifts based off the changes of the position throughout your lifts. So another example of this is going into the elbow flexion, so doing a bicep curl. So greater torque at mid-range angle, so when that forearm or that moment arm is going to be at the longest, longer forearm increases the torque demand, and explains the difficulty of different range of ROM is just range of motion, so the different positions. So it might be easier to curl up from a certain position than the others. So being able to apply this knowledge of torque to exercise and biomechanics. So if the force doubles, the torque doubles. If the moment arm doubles, the torque doubles. So this concept explains why certain portions of an exercise may feel more difficult than others. It highlights the importance of understanding strength curves. Exercises can be modified to match these curves to help improve efficiency and effectiveness. In applied settings, we as practitioners, we can manipulate the torque by adjusting the resistant placement. So where you're holding the weight, where the weight or resistance is going to be, the amount of weight, the amount of force, whether we're going to be adding a dumbbell, adding some extra weight, or just going against gravity or doing our body weight, changing the joint angles. And then the movement techniques. For example, holding a weight further from the body increases the moment arm and therefore increases the torque demand, making the exercises more challenging. So if I'm going to be working with someone, maybe a simple standing core exercise with an elderly individual who is having to work on that. So or having to work more on upper body stability, doing a mixture of different goals in mind. So a very simple one that we can do is holding a weight in front of us, holding a dumbbell on either side while having to stand stationary. So the further you lift that weight away from you, you're going to feel your abdominals increase. You're going to feel your your shoulders. You're going to feel that you're going to feel more force being applied into your muscles. You're having to withstand the gravity, being able to hold that weight in that static position. And again, the further away from your body, the harder it's going to be. So again, that's how it's going to make the exercises more challenging. Another example is with push-ups. So if someone is unable to do a traditional push-up on the floor, what we can do is do the wall push-ups. So we're reducing that moment arm, that angle as well, and so doing it on the wall at that angle versus having it parallel against the floor. So that's how we can modify and work on improving things to kind of work towards strengthening and progressing with someone based off the torque in the axis. So knowledge check. So going over torque. So what increases torque more? Heavier weight or longer lever? So think that over. So far, we've covered force and torque and how this translates into movement within the human body and outside the body, but now we're going to go over levers. So the human body operates as a system of levers, and that's what translates the muscular force into movement. So that's how we're getting the movement and the amount of force, the amount of torque that is able to be applied from the lever systems here. So a lever has three components. It has a fulcrum, where the joint axis is, an effort, so the muscle effort, the muscle exerting the force, and then we have resistance or load, whether that's an external load, like this example here where we are holding something in our hand, so that's the load that you're having to hold that up, or it could just be body weight against gravity or something more external. And then here is just another example of over here the lever components, and then how we're going to go into the different types of levers and the different types of levers, their strength, their weaknesses, and just how those are different based off where the effort, the fulcrum, and the load lie. So to start off, we have our first class lever. Our first class lever is where the fulcrum is between the effort and the resistance. So remember, the fulcrum is your joint axis, and then the effort is going to be that muscular force, and then the resistance, that external or force, whether the load, gravity, of that nature. So a good example here is cervical spine extension. So starting off with your head downward and then having to extend your neck upward. And so you have your fulcrum, that joint axis being your cervical spine. The load is going to be your chin as you're going down and then back up. And then the effort making this happen is going to be your muscles. It's going to be the muscles along your cervical neck area. Another great example is extending your arm for a tricep extension. So you have your triceps, your elbow, and then whether you're holding on to a weight or just moving your arm, that is going to be this is going to be your resistance, your fulcrum or your joint axis, and then your effort or your muscle force. So the joint axis is in between as you're extending your arm, doing that tricep extension. And now we have a second class lever. So a second class lever is where the resistance is between the fulcrum and the effort. So again, the fulcrum being your joint axis, and then the effort being that muscle force. And this, there's different examples that I have listed here. So just like a plain picture of how it's kind of laid out. So you have the fulcrum, the axis on one side, and then the load in the middle, and then the force on the opposite end. Within the body, this is seen whenever doing plantar flexion during a calf raise, having to lift yourself up. The axis being So you have your axis, and then you have your effort, and then the fulcrum. So, or the axis of the fulcrum is going to be on one side, while the load is in the middle, and then the effort on the other end. And then a good example to kind of help keep this, kind of picture this, what a second class lever is a wheelbarrow, classic wheelbarrow. So you have your fulcrum, that wheel on the end, your load or whatever you're piling in the middle of the wheelbarrow, and then your effort. So right here where you're having to lift it and then push that effort to, and then start that movement to push the wheelbarrow. And so the second class lever provides a mechanical advantage for force production, because if you remember that when the moment arm is shortened, then there is less torque to overcome. There is, you have that mechanical advantage. So you have the load right here, and then the moment arm is going to be that perpendicular distance from the axis. And so your fulcrum, so let me put this in a different color. So your moment arm is going to be shortened right here versus when the fulcrum was in the middle and the load on the other side. So the moment arm is shortened, and so you have that mechanical advantage. This is how you can move a big amount of items, of things, with minimal force. Now we have our third class lever, which is where you're going to have the effort between the fulcrum, the joint axis, and the resistance. So a great example of this is just a pair of tongs, where you're having the load, what you're picking up at the end, your effort having to squeeze down on the tongs, and then your fulcrum, that joint axis at the end. Within the human body, this is seen within a bicep curl. So you have your fulcrum, your joint axis at the elbow, your effort from the biceps brachii attaching and then pulling up in the middle, in between that and the load, your dumbbell or whatever you're using to curl upward. So this third class lever is most common in the human body. Most of human movements rely on third class levers, which unfortunately operates at a mechanical disadvantage. This means for greater muscular force is required to move a load. However, this design allows for faster and more precise movements. So again, remember, this is going to be a mechanical disadvantage because that moment arm is going to be lengthened. So that moment arm is going to be perpendicular to that joint axis. And so that joint axis perpendicular and then going from our load. And so that moment arm is going to be higher. It's going to be longer than it is with our other levers, which is why this is technically at a disadvantage. However, again, this allows for faster and more precise movement, so there's a trade-off in what you have to consider during training and during your exercise prescriptions for your patients or your clients. And now we're going to go into mechanical advantage. So with the three different types of class levers that we've already gone over, each one has its own mechanical advantage, and then the mechanical advantage can be manipulated within each lever. So mechanical advantage is determined by the ratio of the effort arm to the resistance arm. When the effort arm is longer, less force is required to move a load, and so you have mechanical advantage. When the resistance arm is longer, more force is required, so now you have mechanical disadvantage. The human body typically favors the mechanical advantage to enhance movement velocity. So effort arm is going to be that physical distance. Here we go. So that physical distance between your lever and the fulcrum where the effort is applied. So here we have an example for the effort arm. And then the resistance arm is going to be between the resistance force, or that physical distance between the physical force and then your fulcrum, or that axis. So that's going to be our resistance. So we have our different class levers that we've gone over. So you can see by here how you'll have different distances of the effort arm and the resistance arm, and how each one can have different advantages, especially when you move the resistance closer to you or away, so you can see how each one will have advantage or disadvantage based off the mechanical advantage formula here. So far you should be able to identify a lever the lever class in a push-up. identify the lever class in a squat, and then be able to discuss the mechanical implications, so the advantages or disadvantages of them in the levers. And so a little knowledge check: which lever class is most common in the body? Now we're going to transition into balance and stability. So balance is maintaining equilibrium, while stability is being able to resist disturbance to maintain the equilibrium. So for example, you can have someone who is balanced, like they're able to maintain equilibrium at status quo, but they can be unstable. So for if they lose their footing, or if someone brushes up against them, they may be unable to resist that disturbance, and so they are unstable. And then you can have the opposite end when you're unbalanced and unstable. So a lot of times in athletic or exercise settings, or working with patients, different clienteles, the stability is often intentionally challenged to improve neuromuscular control. So this can be by having someone, if they are able to and it is safe, standing on a Bosu ball. So standing on one that has that intentionally uneven balance. For our older adults trying to improve that stability and that neuromuscular control, maybe it's having them stand on a pillow or a cushion, something that's going to be more resistance to, or more going to change more often with changing and shifting weight. And so being able to maintain equilibrium with that disturbance of that foundation. So being able to test the stability and strengthen that. And then what's going to affect someone's stability and their what's going to affect their stability and their balance will also be their center of gravity. So center of gravity is going to be the point where of evenly distributed mass. And so a lower center of gravity increases stability, but this is going to be shifting constantly during movement. And so base of support, also known as BOS, is the area beneath the body. A wider base of support increases stability, and then the line of gravity must remain within the base of support. And so again, wider base of support increases stability. You see this with a squat. So if you perform a squat with your feet closer together while having to hold onto a heavy load, having to squat down into that position, you may be a little bit more unsteady, especially if your body is not trained or practicing that movement. While having that wide base of support, you are now at a more advantage with that center of gravity being where it is, and then you're able to withstand that movement and maintain the stability as well throughout the exercise. There are four main factors that can affect stability. So your body mass. So your body mass can alter your body's center of gravity and increases the physical effort required to correct postural sways. And then the height of the center of gravity can affect stability as well, because remember, lowering the center of gravity enhances stability and reduces the likelihood of displacement. Friction affects stability. So friction is the force that results from the resistance between the surface of two objects moving against each other. So whether you are running on ice or running on cement. So when you are running on ice, there is reduced force, there is reduced friction. Or running on cement, running on a hard surface, hard smooth surface, that increases the ground reaction force, and so there is reduced friction. And then alignment, so positioning your central mass securely over your base of support. This minimizes the muscular work required to resist gravity. So that's why if you've ever had depending on where you work and what you do, if you've ever had to do any type of body mechanics and work and go over proper body movements, moving or lifting heavy objects, we want you to carry a heavy object close to your body, close to your center of gravity, your center of mass, versus out in front of you. Because when you hold it out in front of you, now your center of gravity is now adjusted, and it's no longer, and that height is adjusted, and now it's going to be harder for your muscles to work, and increases the risk of displacement for certain joints, and it just places more effort onto your body. While bringing that center of mass securely over your base of support, over your foundation, that minimizes that muscular work required, again, to resist gravity. And now dynamic stability, as I mentioned earlier, dynamic stability is stability during movement. It requires neuromuscular control, so your ability to maintain that equilibrium despite that change in your status. This is critical in sport performance, and then also with aging populations, being able to improve that neuromuscular control so that way they can be able to withstand whether they're all of a sudden, if they lose their footing or they step on something slippery, being able to maintain their stability and prevent a fall. And so dynamic stability is something that we are constantly working on, young or old populations, but it is very common, especially here in sport performance, because that's how you're going to be able to have those quicker reactions and faster movement times. So knowledge check, stability. So why does lowering your stance improve the stability? Keep in mind your center of gravity. What did we discuss so far about that? Now we're going to dive into momentum. So momentum describes the quantity of motion possessed by a body and is influenced by both mass and velocity. So linear momentum, it refers to motion in a straight line. Greater mass or speed produces greater momentum, and it influences collision forces. So we have linear momentum, but we also have angular momentum. So this refers to the rotational motion around an axis. Angular momentum is particularly important in activities involving rotation, such as throwing, jumping, or changing directions. With momentum, so typically in human movement, both forms of momentum, linear or angular, are often presented simultaneously. So for example, when you're running, you have that forward linear momentum moving forward into that straight line. However, the limbs are generating that angular momentum through rotational movement along your joint axis, like at the elbow as you're pumping your arms, at the knees and your hips as you're moving those legs propelling forward. Increasing either your mass or your velocity increases that momentum, which can enhance performance, but it also increases the demands placed on the body to control the movement. So for example, a faster sprint generates faster momentum, but there's increased muscular effort to decelerate safely. So being able to control the momentum is essential for safe and efficient movement. Another example is when you are jumping and being able to, during the landing, the body must absorb and dissipate the momentum to prevent injury, to prevent that shock traveling up into your joints, into your knees, into your bones, and causing injury or causing damage. Failure to do so, failure for your body to be able to absorb and dissipate that force, like with that jumping for this example, can result in excessive loading and loading on your joints and your soft tissue. Now, during movement, your body is constantly having mechanical loading. So which is the forces applied to biological tissues and which are constantly being subjected to this during movement. So this mechanical loading influences adaptation, so your body's ability to progress and get stronger, become more efficient, have whether it's hypertrophy or more neuromuscular control, having those adaptation in places to withstand the mechanical loading and prepare for it for the next time. However, it can also influence injury. So too much mechanical load that the body is unable to overcome can result in strain and injury in our muscles and our soft tissues as well. So there are 6 types of loadings. So we have compression, which is 2 pushing opposing forces that squeeze on an object trying to compress it. We have tension, which is 2 pulling opposing forces trying to stretch an object, trying to pull it apart. We have shear, so 2 pushing or pulling adjacent forces acting close together but not directly opposing each other. And then we have torsion, which is also known as twisting, which is created when a force is applied to a structure and makes it deflect at an angle or twist. And then bending, when force is applied to a structure that is fixed on both ends, and when that force is applied, that causes it to bend. Now, with the mechanical loading, we're going to have stress and strain. So stress refers to the amount of force applied to a tissue, while strain refers to the deformation that occurs as a result of that force. So the relationship between stress and strain is illustrated by a stress strain curve, which we're going to go further into. It just describes how tissues respond to the loading. But the stress versus strain, this can either lead to adaptation, so your body progressing and recovering and building itself stronger to become more efficient, or a failure where you're going to have some significant injury or damage to the tissues or soft tissues. So going into this stress-strain relationship and how it's displayed here or illustrated as a curve. So this curve has three different portions here. There's the elastic region. This is where the tissues deform but return to their original shape when the load is removed. And then the plastic region, where there is some deformation that is occurring, which may, even when the load is removed, which may indicate some tissue damage. However, if the load continues beyond this point, then you could have tissue failure and injury can occur. So this is how we can have, where using this relationship, this stress-strain relationship, it's how we can go about progression when it comes to exercises and being able to work on building that strength or that endurance for someone, because we want to find that sweet spot, because we don't want to get to that point of failure, but being able to have like micro damage to the tissues, that have where it's like breaking down and then it's rebuilding stronger to form more actin and myosin to be able to produce more cross bridges, create stronger force within the muscles. We need to get slightly within that plastic region. However, again, we're trying to make sure that we are being safe and effective, because it can go too far. That's how you can also have someone have a strain versus a tear of a tendon or a tear of a ligament. So being able to make sure that you are having proper mechanical loading. So we are focusing on that tissue adaptation without inciting damage or injury to the muscles. So for example, resistance training. We're applying controlled stress to the muscles and connective tissues, leading to the increased strength and resilience of those muscles and tissues. However, excessive and improperly applied can lead to overuse injuries if we're not careful. And this slide is going a little bit more into that, where we're going to have adaptation versus overload. So progressive loading promotes adaptations to the tissues where they're building that resilience and that strength, but excessive load can increase your injury risk. All right, knowledge check. So which loading type occurs during an ACL injury? Alrighty, and now, so at this point, you should be able to modify joint angles to adjust torque, control velocity to manage momentum, be able to adjust someone's base of support to influence their stability. So being able to be a little bit more specific and tailoring when creating an exercise prescription with a biomechanical specific view in mind as well. So a summary, force produces torque, levers determine the efficiency, balance influences stability, momentum affects impact, and mechanical loading drives adaptations. So next up, we're going to transition into joint-specific analysis. So we're going to be able to apply mechanics to specific joints and then integrate structure with our biomechanics thus far. And here are our references. Let me know if you have any questions about the material today.